reminder, the last day to withdraw is Wednesday, November 22nd. If you are concerned about your status in this course, please see me. The ACS final exam does have a study guide that's available. You can check it out. I think it has to stay in the library, is my recollection, and I'm pretty sure it's at the reference desk. What I will tell you, though, about it is that it is a study guide for a full year exam, not a single semester exam. So you're going to pick it up and you're going to see some stuff like on acid-base chemistry and on kinetics and everything else that you haven't done. But about half the questions on there are first semester type questions. There's not a special first semester study guide, but you can check it out and look at it, and that will give you some idea of the types of questions that you will find on the final exam here in this course. So any questions that you have? Okay, you came in here today, let's see, after I passed out the periodic tables, you can take that, that's it right there. If you came in late, there's some extra periodic tables up here or in the back. We are going to be writing on the periodic tables today, so make sure you have those out. The other thing you want to have out is we had a handout here the other day. Actually, there was two handouts, and very conveniently, the one tucks inside the other. Anybody not here the other day and need a copy of the handout? Anyone? Okay. So, with that said, let's go ahead and pull out that handout. And I believe, oh, this is not on the handout. That's okay. I don't think so. All right, but one of the things that we did in here on Tuesday is we demoed a bunch of line spectra. And you recall that the line spectra are something that is different from element to element. In fact, on your Socrative app questions today, the first one on here was the emission spectra or line spectra the elements are, and we should have answered that they are different from each other. And central to the stuff that we're going to be discussing here next, these next few questions are also relevant today. So the frequency and wavelength are, and these are inversely proportional to each other. And next, frequency and energy. These here are directly proportional to each other. And finally, the wavelength and energy. These here are inversely proportional to each other. So today here, as we're looking at some of these items as we begin, our understanding of that's going to be rather important. So we're going to start by looking at the Bohr model and the emission spectra, and we want to come up with an explanation as to how or why we observed the emission spectra the way we did. And this was first explained by a scientist by the name of Niels Bohr, and Bohr offered up his explanation in about 1911. And I'm sure I mentioned before in here, we don't test on names and dates, but it's a good idea to have an understanding as to kind of what the chronology is. But Bohr came up with this explanation. And what Bohr said was that the energy of the electron was quantized. So again, Bohr came and said that the energy of the electron was quantized. And what that means is that the electrons could only have certain very specific energies and not any others. And the way that Bohr envisioned the electrons in an atom was something like this, where this here would be the nucleus, and then the electrons circled the nucleus, kind of like the planets might orbit the sun. And so again, the electrons could have been thought of as being somewhere in these orbits. Now, ordinarily, those electrons would like to be in their lowest state of potential energy. And if we went back and did a really quick explanation of this, what kind of charge does the nucleus have?
Positive.
Positive. And the electrons have a charge that is negative. And of course, when we have opposite charges, what do opposite charges like to do? They'll attract each other. And whenever you have a couple objects in a field of force, we have what's called potential energy that is possible. And it's very similar to this block of wood here, which is being attracted to the ground, and actually it's being attracted to everyone else that's in here. But the Earth has the greatest attraction that's being exerted on this block of wood, and of course then if I let go of it, the block of wood will drop back down. When it drops back down here, we say it's in this lowest state of potential energy. And we can give it more potential energy by moving it further off the ground. So whenever you have a couple objects that have an attraction for each other, the greater the potential energy we have would be due to its being positioned further off the ground. And the same is true with electrons in atoms. Ordinarily, they'd want to be in their state of lowest potential energy. And consequently, this position here, when we show this electron in this orbit, this position is referred to as the ground state, which is the lowest state of potential energy for that electron. Now, what can happen is that we can put this electron into a higher energy state. And we can put it into a higher energy state by putting some energy into it. If it's the block of wood, we lift it up. I'm putting some energy into it. If we're dealing with electrons and atoms, that energy could come by running some electricity through it, like we did the other day, or by spraying it in the flame, like we did. And whether we did one or the other, then, what happens is that that atom would absorb some energy, and when it absorbs some energy, that electron would get promoted to a higher energy level. Well, once it gets promoted to a higher energy level, which, by the way, the name of this state is referred to as an excited state, that electron is not stable in that excited state. And what happens then is that electron will drop back down to a lower level. And when it drops back down to a lower level, it gives off energy in the form of light. And each jump here corresponds to a different wavelength. So when we saw a jump from the third energy level down to the second energy level, we would observe that, and this would have been now for the hydrogen atom. So this would be the emission spectrum for hydrogen. So again, this would have been the emission spectra for hydrogen. And so when the electron jumped from the third level down to the second, that corresponded to a red line. If it jumped from the fourth level down to the second, we would have seen that as that bluish-green line in the spectrum. And then the jump from the fifth down to the second would have been the violet line. Now, there's many, many more jumps that occur. You might wonder why we're talking about jumps down to the second. Well, that's because those are the jumps that are actually in the visible portion of the spectrum. And the one thing I don't like about this particular diagram is it's not drawn properly to scale. The correct scale should look something like this. And if I was going to draw something in my notes, this is how I would do it. I would show the nucleus. The first level might be out something like this. The second level maybe here. The third level is something like this, and the fourth level is going to be even closer to the third level. So what actually happens is as we go away from the nucleus, the levels actually get closer and closer together, rather than this model here, which again is drawn very poorly. It's not drawn to scale. It actually appears that as you go away from the nucleus that the levels are getting further apart. And so in this particular model here, you actually get out to a point here where this is probably about where infinity is. Okay? So the levels get gradually closer and closer together as we get further away from the nucleus. And the reason why we talk about them always jumping down to the second level, at least in the visible portion here for hydrogen, is that that jump happens to correspond to wavelengths of light that are in that visible portion of the spectrum that you and I can see. Turns out that a jump from the fourth level down to the first, this jump is too large. This would be one that has a greater amount of energy, and a greater amount of energy is going to be one that corresponds to a shorter wavelength. Because as you came in here, the relationship between energy and wavelength is an inverse relationship. So the greater the energy, the shorter the wavelength. Okay, so the greater the energy. So this jump here, fourth down to the first, would have more energy than, say, one from the fourth down to the second. And if it's of a shorter wavelength, that shorter wavelength is going to sit somewhere out here. That's going to be outside the visible spectrum, and it would wind up being in the UV portion of the spectrum. Likewise, there's a whole bunch of jumps that occur here, and this is not drawn to scale. But if we look like from a jump from the fourth to the third, which would be like right here to here, this is going to be one that's a really small jump. And a really small jump is going to correspond to one that is a longer wavelength, because again, energy and wavelength are inversely proportional. And with a shorter, what's that right? Shorter jump. So less energy means the wavelength is going to be longer. Then those wavelengths that we would observe, say, to the third level are going to sit out here, which is going to be in the infrared portion of the spectrum. So it turns out in the case of hydrogens, the jumps that we're seeing are the ones that occur as jumps down to the second energy level. But what happens with these electrons is they're in continual movement. They'll go up to one level, drop down. They might only drop down to the second. They could absorb some more energy, maybe only go up to the third, drop down to the first. So they're continually transitioning between all the levels within there, and each transition corresponds to a different wavelength. And that's why we see very distinct lines that are in the spectrum. That's why we can put a model up here, and this model that you're observing is going to be identical to the model that we observed in here the other day, because according to Bohr, the energy of the electron was quantized. And we say that something is quantized, that means that only certain very specific values are allowed and nothing else. So kind of an analogy to that, if, let's say, the speed of your car was quantized. The speed of your car was quantized, that might be like saying that your car could only travel at 10 miles an hour, 20 miles an hour, 30 miles an hour, and those are the only speeds it could travel. And it couldn't travel any other speed. So if you went from 10 miles an hour to 20 miles an hour, you would do so instantaneously. And so that's kind of like what, again, these quantized energy levels are within the atoms. Now what's kind of interesting about this is that these jumps between these quantized energy levels had a name. Anybody know what that name is? They are called quantum leaps, or quantum jumps. So these jumps of these electrons between these quantized energy levels was referred to as a quantum leap. Now, of course, if you've heard of quantum leap before, where have you probably heard of it?
Science fiction.
Yeah, science fiction. When quantum leap is used in science fiction, what does it usually imply? Time travel, exactly. And so that's kind of where this whole idea came from, the thought of the quantum leap. And the reason why it became associated with time travel is this, is that, again, the energy of the electron is quantized, and in order to get from one energy level to another, it has to do so instantaneously. And when we say instantaneously, it doesn't mean that it's like you could see it travel. It means it immediately goes from one to another, and it can't exist anywhere in between. So again, that's where the whole idea where sci-fi adopted this idea is that in order to go from one level to the next, it couldn't exist anywhere in between once it got from one place to another. So when we think of it in science fiction, we think of these huge jumps across space and time, when in reality the term originated from these tiny jumps between these quantized energy levels in the atom. Now, one of the biggest weaknesses of the Bohr model of the atom was that it really only worked well for hydrogen. And it worked well for hydrogen because hydrogen contains one electron. So as long as we're dealing with one electron, we could explain it fairly well. Once we got up to helium with 2 electrons, lithium with 3 electrons, and so forth, then this explanation began to break down. The other thing that began to break down about it is that when these electrons were viewed as moving in these orbits about the nucleus, what was known at that time is that charged particles that moved in curved paths radiated or gave off energy. And if they're moving and giving off energy, what would happen is that electron then actually would spiral into the nucleus. And something was keeping those electrons out there because they weren't spiraling into the nucleus. We were still observing the same lines over and over again. So what happened then was the development of what's called quantum mechanics. And quantum mechanics came about in the 1920s. This was developed in the 1920s. And it sought to address the weaknesses of the Bohr model and see if there was some other way we might be able to explain it. And the first big breakthrough came with a scientist by the name of Louis de Broglie. And he was a French chemist, and he came up with this idea in about 1923. And he reasoned this. De Broglie reasoned that if we look at light, which behaves primarily as a wave, but sometimes like a particle, and so again we talked about this the other day, light has a dual nature. Light behaves like a wave, but sometimes as a particle. Well, de Broglie had this idea that we've been looking at electrons the wrong way. All along we've been looking at electrons as if they're particles, but we probably should be looking at them as if they were waves. And so his proposal was this. He proposed that these tiny high-speed particles, like electrons in atoms, might have some wave-like properties. And he was onto something because it was within probably about 5, 6, 7 years the first electron microscope was developed. And in an electron microscope, what is done is that particles or electrons are accelerated towards things that we want to examine. It interacts with matter, and we can then look at the patterns by which it interacts with that matter. And so the electron microscope then came about in the late 1920s and early 1930s. But when de Broglie developed his equation, he came up with the equation that looks like this. To show that relationship, it says lambda, or the wavelength, is equal to h over mv. And it was really kind of odd that this constant showed up again in the calculation, but this here is Planck's constant. Lambda here is the wavelength. M is the mass of the particle. And then v is the speed of the particle. Okay, remember that it's not velocity, because velocity also implies direction. So when we see v, v is used as speed, which we're concerned about magnitude only and not direction. So what we can do then is we can calculate wavelengths of particles like electrons, and let's go ahead and do that. Let's calculate the wavelength of an electron moving at 1.15 times 10 to the 5th meters per second. Let's calculate the wavelength of an electron moving at 1.15 times 10 to the 5th meters per second. Now, I'm not telling you which units to put it in, but what I will tell you is that usually when we calculate our answers, we put them in units where the value is somewhere between 1 and 1,000. So whatever that will be, let's go ahead and just calculate where we're at, and then we might need to put it in nanometers or micrometers or something like that. So lambda is equal to h over mv. We start plugging in values. If you don't have your conversion sheet out, let's get it out. We need to find the value of Planck's constant, which is right here, 6.626 times 10 to the negative 34th. Joule seconds. And we're going to divide this by the mass of an electron. And the mass of the electron we should have in here, there we go, 9.109 times 10 to the negative 31st kilograms. So 9.109 times 10 to the negative 31st kilograms. And then the speed, of course, would be 1.15 times 10 to the 5th meters per second. Now, if we start trying to cancel stuff out here, it doesn't look like we have anything that's going to cancel. Exactly, we need to change units. So, the first thing to do is to remember to put these in SI units. And so we come back and ask ourselves, are these all SI units? And yes, they are. I mean, we still need to change them, but they still are SI units. But we'll come back here to this one right here, which tells us what the joule is. The joule is 1 kilogram dot meter squared per second squared. So we'll come back here, and we're going to substitute for the joule a kilogram dot meter squared per second squared. So again, this much right here is the joule. And of course, these were joule seconds. So it'll be joules dot seconds. So now that we've made that substitution, let's see what happens to the units. What happens to kilograms? Cancel out. What happens to meters? Well, we have 1 in the denominator, but we have 2, that is m squared in the numerator. So m squared gets reduced down to m to the first. We have seconds squared times seconds. So this second will cancel out with one of these. Then we have seconds in the denominator of the numerator and in the denominator of the denominator. So what happens here? They cancel out as well. And the units we're left with is meters. So again, we do a quick unit analysis. So as long as we use SI units, what this is showing, as long as we use SI units, we should be in good shape. So let's go ahead and multiply this through. Excuse me?
Yes.
Negative 34. What did I put? Well, why did I do that? That's pretty stupid. That's negative 34. Okay? So, 6.626. See, I'm going to catch up on my sleep tonight. There's no school tomorrow. Don't forget, there's no classes on campus tomorrow. If you show up here tomorrow, you'll be all by yourself.
With other people that forgot.
With other people that forgot, probably. Do run this through your calculators, because I know that I'll see all sorts of mistakes on this. And I am getting 6.3 6.33 times 10 to the negative ninth meters. Now again, when it comes to wavelengths, usually the number we write out front here in front of the unit with wavelengths is going to be a number between 1 and 1,000. Well, this isn't a number between 1 and 1,000, so we need to convert it to the units that would give us a number between 1 and 1,000. So that best choice would probably be units of nanometers. Every 1 nanometer is equal to 10 to the negative ninth meters. Well, ain't this convenient? Meters and meters cancels, 10 to the negative ninth cancels with 10 to the negative ninth. And we wind up with an answer of 6.33 nanometers. So I do know that in your textbook it will probably specify the units. Come exam time, just so it's not ambiguous, we'll ask you to answer them with a specified set of units as well. So any questions that you have on these? All right. Well, quantum mechanics from here went to some work by two other scientists. One of them was the name of Werner Heisenberg. Now see, if I would ask my students 10 years ago who Heisenberg was, they'd have no idea. But now you know, because where have you heard of Heisenberg? Breaking Bad, right. Breaking Bad. The lead character in Breaking Bad, which by the way, I don't condone necessarily the subject of that show, but if you want to have one, in my opinion, is some really good writing. And the chemistry in there actually is good too. With the exception of about the first 1 or 2 episodes, they're talking about hydrofluoric acid, and they spelled hydrofluoric acid wrong. Okay, but other than that, they fixed it. On the same later episode, you can see that they have the vats of hydrofluoric acid out there, and they have it spelled FLUO. But the first episode is FLOU. Okay, so, but coming back here, I digress. Heisenberg was known for the uncertainty principle. And we are not going to deal with the mathematics of the uncertainty principle, but mainly because it does take a background in multivariable calculus and differential equations. And how many of you have gotten that far? Tanner? Okay. Right. So, but if we were that far along, what the mathematics would show is that it is impossible to simultaneously determine the speed and the location of an electron. If we learn something about the speed of the electron, we don't know anything about its location. If we learn something about the location of the electron, we don't know anything about its speed. And so what the Heisenberg uncertainty principle basically showed is that this model is too predictable. Okay, that's kind of the essence of it, is that the mathematics showed that this model is too predictable. So it can't be valid. There was a work of another scientist, the name of Erwin Schrödinger. And Schrödinger,
Do you have to remember these names?
excuse me? Schrödinger also worked in 1927, and again, we don't worry about names and dates. I write them down to give credit where credit's due, and just to kind of put it into proper chronology. But he used the ideas of Heisenberg and de Broglie and developed what's called the wave equation. And in the wave equation, Schrödinger treated electrons as if they were waves. Again, the mathematics behind it, very complex. You are not going to be accountable for the mathematics of it because we're not even going to go through it. But what you will be accountable for is knowing the outcome of the Schrödinger wave equation, which is right here. And this will be probably the first page in that packet of your handout. So this you do need to know. And we're going to fill in the blanks here and provide some necessary information. So here's how the Schrödinger wave equation works and what you would need to know. First of all, the Schrödinger wave equation, instead of describing electrons being in orbits, described electrons as existing in orbitals. So again, not orbits, but orbitals. When orbital is defined as being a region in space where there's a high probability of finding an electron. So again, did not describe the electrons as being in orbits like they were in the Bohr model, but rather being orbitals, which is a region in space where there's a high probability of finding an electron. And now the equivalent to that might be something like talking about pitching or throwing a bunch of baseballs. If you were to track the paths of baseballs, pitch after pitch after pitch, you would find that there's going to be a greater concentration in one area than there is in this area as compared to this area out here. So again, there's going to be a whole bunch of them that are going to be concentrated here in the center. So this would be described as being a probability plot. Okay, in areas where you see it more densely shaded is areas where it's more probable of finding an electron. Areas where it is less densely shaded would be areas where it is less probable of finding an electron. Or in the case of this, finding where that baseball is going to wind up. And so if we'd kind of encompass where that's located, that shape would wind up being a shape that would be examined something like this. So if we were to plot in 3 dimensions how the electrons would wind up being located, turns out that 99% of the time they'd be located in a volume something like this. But the details of where they're located we don't know, because again the Heisenberg uncertainty principle tells us that we don't know those details. If we were to figure out something about its speed, we wouldn't know its location. If we were to figure out its location, we wouldn't know its speed. Well, we can say though that it's probable of finding an electron somewhere in that space. Now another analogy I like to use is that of a spinning bicycle wheel. Okay, so if we take a bicycle wheel and spin that around, what would happen is that those spokes would fill up a volume. And we could say that it is probable of finding a spoke somewhere in that volume. In areas where those spokes are a little bit closer together, it's probably going to be a little bit more probable of finding them than somewhere out here. Now one of the things I used to do growing up in our neighborhood, we would always take the bikes. I don't know if I told the story before, but we'd turn the bikes upside down and we would spin them around really fast, and then we'd start throwing rocks through them. Okay? And then, you know, the whole idea was to try to get the rocks to go through, which they did most of the time. But then every now and again, what would happen is they would find a spoke and they would kick the rock out. Okay? Lots of fun if you've never done it before. Okay? The youth of today are very underprivileged. Okay? This is what we do out in the country growing up. Okay? Kind of boring. Right? So we did that, but it fills up the space just like electrons would fill up the volume, much like this here. And if we went down a little further, we could do the same thing with a vibrating string. If we took a string and plucked it, what would happen is that string would vibrate back and forth and fill up a volume. And we might say that that's kind of equivalent to an electron that's in an orbital something like this. But if we have vibrating strings, they don't always vibrate in the same type of pattern. We might have a vibrating string that would vibrate in a pattern like this and have 2 different nodes, so to speak, and that would be equivalent to an orbital that has a shape something like this right here. Now, if we have some music people, what is the difference between these two if we listen to these two? How different do these sound?
That one's lower pitched and the one on the bottom is higher pitched.
Right, this is the lower pitched one, this is higher pitched. You know how to...
I did this in physics.
Yeah, can you demonstrate?
No.
All right. Well, I'll try. I don't sing very well, but if this one is all right. So that would be the difference when we talk about pitch. It's not the volume, but we talk about the pitch. It goes something like that. And in physics, we would describe that as being the frequency. Right. We describe it as being the frequency. Which one of these two has a greater frequency? Right, the bottom one has a greater frequency. Now if you remember, one of the things we discussed the other day is the relationship between energy and frequency. And what is that relationship? It's a direct proportion. Energy is directly proportional to the frequency. Now if we go back and look at these, we can also look at the wavelength. Which one of these has a longer wavelength?
The first one.
Right, this one here is a longer wavelength. So with this one being a longer wavelength and this one down here being a shorter wavelength, as we started with today, what is the relationship between wavelength and frequency? It's an inverse proportion. So we can kind of make some conclusions then about this, is that the energy is inversely proportional to the wavelength, or vice versa. But what's going to be pretty important here is this relationship of energy to the frequency. And so again, this one here has a greater frequency. And if this has a greater frequency, this one means it has a greater energy. Exactly. So we go back then to our handout, and it says that there are two main factors that determine the energies of electrons that are found in orbitals. One of them kind of goes back to where we started with here today. What happens to the potential energy the further we get away from the nucleus? It increases. It gets bigger. So the further we are away from the nucleus, the greater the energy. So we can say that one of the things that the energy of the electron depends on is the size of the orbital. Where is it? Here we go. One is the size of the orbital, and the other one is the shape of the orbital. And if we think about these now for a minute, again, what we say about the energy, the larger the orbital is. It's greater. So larger orbitals have greater energy. And I thought I closed this. I guess I didn't. Okay. So larger orbitals have more energy than smaller orbitals. And then if we go back to the diagrams we just looked at, again, which one of these here has more energy? The bottom one. So if we looked at these orbitals right here, which one of these two orbitals has more energy? Yeah, this one right here. And if we compare these two, which of these has more energy? Yeah, right here. And so then we'd say that the more complex the shape, the greater the energy. So again, those are the two main determining factors of the energy electron. One is the size of the orbitals, the other is the shape. The greater the size, the greater the energy. The more complex the shape, the greater the energy. And again, think back to these diagrams here. The more nodes this has, the greater that amount of energy. Now, the other thing that the Schrödinger wave equation did was this. It showed that each electron in an atom may be defined by a set of 4 quantum numbers. And those 4 quantum numbers are N, L, M sub L, and M sub S. And they stand respectively for the angular momentum quantum, the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. And these quantum numbers all have a set of rules associated with them. And so you'll be responsible for knowing these sets of rules. First of all, the principal quantum number n. N here determines the overall size of an orbital and defines what we call the energy level or energy shell. And n can have values that go anywhere from 1, 2, 3 on up into infinity. So it can only have integer values starting at the number 1. So if we go back to our Bohr diagram, this would be just like those principal quantum numbers. That is, as we go away from the nucleus, the values get larger. So bigger n basically means bigger orbitals, more energy. Right. The second quantum number here is the angular momentum quantum number. And we call that L, or label it L, and this determines the shape of the orbitals. and defines what we call the energy sublevel. And L has values that go anywhere between 0 and n minus 1. So that is, if we looked at L could be 0, 1, 2, all the way up to n minus 1. When we have an L value of 0, we say that it belongs to an S sublevel. When L is equal to 1, we say that an orbital belongs in a P sublevel. When L is equal to 2, we say that an orbital belongs in the D sublevel. And when L is equal to 3, we say it belongs in an F sublevel. Now L doesn't stop at 3. L does keep going. If we went on to 4, we say that they belong in a G sublevel. And if we go up to L is equal to 5, then they belong in an H sublevel. So up to this point, S, P, D, and F, they're not alphabetical. These letters S, P, D, and F come from descriptions of the line spectra. So for example, D is diffuse, F is fundamental. So it has very specific descriptions to the types of lines that we see in the line spectra. But once we get up to F, then the letters go alphabetically, so it'd be F, G, H, and so on once we get up to that F sublevel. So now as you look at these here, this would be an orbital that is in an S sublevel. These are orbitals right here. These three are ones that belong in a P sublevel. And these 5 right here, these are orbitals that belong in a D sublevel. So again, each one of these models here represents a different orbital. This is an orbital, this is an orbital, this is an orbital, this one is an orbital down here. And this is an orbital in a S sublevel. These are orbitals in a P sublevel. These are orbitals in a D sublevel. Yes?
You said L and P, so it will start going alphabetical after F. Does
Yes.
it end at Z, or does it keep going on with different things?
Well, it turns out that they're pretty much meaningless after we get up to about H. Okay? So, and it's just like the energy levels when we get going away from the nucleus, those energy levels kind of get squished closer and closer together. The same is true once these values of L get bigger, the shapes get to be so complex or whatever that they become almost meaningless at that point. Okay. Now, the quantum number m sub L is called the magnetic quantum number. And m sub L, this defines the orientation of an orbital within a sublevel in three-dimensional space. And so what that means is that the possible values of m sub L can be integer values anywhere between negative L and positive L. So here's where or what these things mean. Let's go back to an S sublevel. If we have an orbital in an S sublevel, that means that L is equal to 0. If L is equal to 0, the only possible value that m sub L could have is 0. Since it can only have one value, we only find one type of orbital in an S sublevel. If we go to a P sublevel, in a P sublevel, L is equal to 1. When L is equal to 1, that means that m sub L could be negative 1, 0, or positive 1. In other words, how many different values could we have? There's 3. And because we could have 3 different values, that means we can have 3 different orientations in three-dimensional space. Which should make sense because if a p orbital lies along the axes, and we have 3 axes, one will lie along the x-axis, one will lie along the y-axis, and one will lie along the z-axis. And those then describe the 3 orientations along the axes. If we go on to where L is equal to 2, then we say we are in a D sublevel. If we're in a D sublevel, m sub L could go anywhere from negative 2 up to positive 2. How many different values do we have here?
5.
There's 5. And if we have 5 different values, that means that we are going to have 5 different shapes or 5 different orientations in three-dimensional space. And if you look at these are all different. This one here is on the XY plane. This is on the XZ plane. This is on the YZ plane. This one here goes back to the XY plane. But if you look at these two and compare them to each other, notice now that this one has lobes that are between the axes. This one has lobes that are along the axes. So in three-dimensional space, these are not going to overlap with each other. And then if we go down to this one here is one that lies along the z-axis. Well, it looks like this little disk might in fact overlap with some of these spaces. Remember that this is a probability plot, and this is actually going to wind up filling in some space here that we just don't see the holes in along these planes right here. So again, these are the different axes and the different orientations with the D's. Now beyond this, I don't have models, but if we want to look at some models, I did have a website that I posted up to our D2L today. But if we wanted to look at some of these, let's say we want to look at the F orbitals. Now, if we're looking at an F orbital, remember F orbitals belong in the F subshell, in which case L is equal to 3. If L is equal to 3, that means that M sub L can go anywhere between -3 and +3, which means it has a total of 7 different values. So there's going to be 7 different orientations. And if I come back and look at these F orbitals, there's 1, 2, 3, 4, 5, 6, 7. And if we went on to the G's, G's, of course, would be when L is equal to 4, which means M sub L can go anywhere from -4 to +4, which means it could have a total of 9 different values. With 9 different values, we should be able to come back here and show that there's a total of 9 different G orbitals. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 different orbitals. And again, you see, the question came up is what happens if we keep going? They get to be more and more complex. After a certain point, that's just rather meaningless to look at. So, any questions on these? All right, then the last quantum number, this one's easy. This one is unrelated to all the other ones. It's called a spin quantum number. The spin quantum number determines the spin of an electron. And if you have a given set of n, l, and m sub l, the values of m sub s, or the spin quantum number, can either be a -1/2 or +1/2. The bottom line, what should you get out of this? This is what you should get out of it. This means that an orbital may hold a maximum of 2 electrons. So again, this tells us that orbitals can hold up to 2 electrons. So each one of these orbitals that you see right here, this orbital here can hold up to 2 electrons. This orbital here can hold up to 2 electrons. This orbital here can hold up to 2 electrons. So that's what the spin quantum number m sub s means. Final thing we should mention, I think we probably already guessed this, and because I've been using it just to describe it, is orbitals within a given sublevel have the same letter designation as the sublevel. In other words, if we have orbitals in a p sublevel, those are called p orbitals. These here are part of a d subshell, which means this is called a d orbital. So d orbitals are in the d subshell, p orbitals in the p subshell, and so forth. So what we're going to do with this now is we're going to try to kind of assemble some of this information. And in your packet here, you have another table we're going to complete. And we're going to start, I'm going to complete the first 3 lines here for you, and then I'm going to give you a 4th line to have you complete and compare your answers. So we are going to start with the lowest possible value of n, which is
0,
1. And then we're going to look at 2. The next value is 3. And then, of course, after 3 would come 4. You're not going to do 4. We're going to skip 4. And we're going to have you do number 5. Okay? So let's work with number 1 here first of all. If n is equal to 1, that means L could have a value of 0. And that's because L can go anywhere from 0 up to n minus 1, which in this case would be 0. So it can go from 0 to 0. When n is equal to 1 and L is equal to 0, we say that the subshell is 1s. And where the numbers come from is that this number goes here, and when L is equal to 0, that determines the subshell notation. Now, M sub L, this can go anywhere from negative L up to positive L, which means M sub L in this case can only have a value of 0. If it can only have a value of 0, that means only one value is present, which means it has one orbital. And because it only has one orbital, that means that that orbital will hold up to 2 electrons. And since there's only one orbital in that subshell will hold 2 electrons altogether. Now if we go to where n is equal to 2, that means L could either have a value of 0 or 1. And so we're going to go ahead and break this up here, going across. The subshell notation for this first one is going to be 2s. Because, again, the number 2 comes from this right here. And when L is equal to 0, that tells us we're in the S subshell. What would the subshell notation be right here? It's going to be 2p. And that's because when L is equal to 1, if you're unsure of this, come back to this. And when L is equal to 1, we say it's in a P subshell or P sublevel. So then, M sub L. Right here, this can go anywhere from negative L to positive L, so the values that are possible here would be 0, negative 1, 0, and plus 1. Orbitals in the subshell would be 1. Orbitals in the subshell here would be 3. And it's 3 because we have 3 different values of M sub L, which means that there's 3 different orientations possible. Number of electrons, 2 and 6. And it's going to be 6 because each orbital will hold up to 2 electrons. So 3 times 2 is going to give us 6. We'll go on to the next one here. We're n is equal to 3. When n is equal to 3, that means L could be 0, 1, or 2. 0, 1, or 2. So now we're going to divide this up into 3 different lines. Subshell notation for the first one would be 3s, next would be 3p, next would be 3d. Then right here, possible values of M sub L would be 0. Right here it would be negative 1, 0, and positive 1. And right here it would be there we go. Orbitals in the subshell going down. The first one would be 1, 3, and 5. The number 5 comes from the fact that there are 5 different values of M sub L. Number of electrons would be 2, 6, and 10. All right, go ahead now. Remember, we're going to skip 4 and go on to 5. Complete this for the fifth energy level. Show all of the subshells, show all of the m sub l values, show the number of orbitals in the subshell, and the number of electrons in each subshell. What is the highest energy sublevel you should have come up with? 5G. And 5G should have a total of how many electrons? 18, right, 18 electrons altogether. And so if you've done it, I mean, you don't have to do all the little busy work writing in every single one, but you should wind up with something like this down here. Any questions on these? All right, then in your packet, we'll go to the next page. And in the next page here, we are going to write out electron configurations. Electron configurations. And the electron configurations tell us the arrangement of electrons in the atom. So this tells us the arrangement of electrons in the atom. And now what's going to be helpful for you is if you have your periodic table out and handy. And we'll go ahead and put one in here. And we want to show how those electrons are arranged. So we're going to start with the element hydrogen. Hydrogen now has how many electrons? Right. Uno, for those that don't speak Spanish, is 1. Very good. So we say Z is equal to 1. The electron configuration for hydrogen is written like this, 1s1. Now what these numbers stand for is this. This number out front, right here, this is your principal quantum number, or n. This value right here designates the value of L, and this superscript right here, this tells us the number of electrons in the sublevel, or subshell, whatever term you prefer to use. And now we read it like this. We read it as 1s1, not 1s to the first. It's not an exponent. We read it as 1s1. After hydrogen, let's look at helium. Helium now has 2 electrons because its atomic number is 2. When we write out its electron configuration, we write it as 1s2. So that tells us we have 2 electrons in the 1s sublevel. Again, it's not 1s squared or 1s to the second. We read it as 1s2. Now if we go on to lithium, lithium has an atomic number of 3. Right here, atomic number 3. That means it has a total of 3 electrons. And so now if we go back to our diagram, remember that the 1s sublevel holds a maximum of 2 electrons. And once we fill that up, there's no more space in the 1s sublevel. We have to go on to the next one, which is the 2s. And since we have 1 electron left over, that means we put 1 electron into that 2s sublevel. So we write it as 1s2, 2s1. And that's how it's read, 1s2, 2s1. Let's go on to nitrogen. Nitrogen now has an atomic number of 7. With an atomic number of 7, that means it has 7 electrons altogether. So we put in 1s2, 2s2. Again, we stop at 2 because the 2s sublevel will hold a maximum of 2 electrons. Once that's filled, we go on to the 2p. And how many 2p electrons do we need? 3 altogether. Can the 2p sublevel hold all 3? Yes, it can, because the 2p sublevel could actually hold up to 6 electrons. So if we went on to sodium, sodium now has 11. Right here, sodium has 11. If we now write out its configuration, we'd have 1s2, 2s2, 2p6, because remember the p's will hold up to 6 electrons. After 2p is going to come 3s. And how many will go into that 3s sublevel?
1.
Just 1. So then we go on to phosphorus. Anybody any questions yet? By the way, what we're using here is called the building up principle. This is called the building up principle. And what the building up principle says or does for us, it says that we try to occupy the lowest energy subshells first before we place electrons into the next highest energy subshell. Again, it's called the building up principle. So we go on to the next one, which is phosphorus. Atomic number here is 15. So if we look at number 15, phosphorus, we'll put in 1s2, 2s2, 2p6. 3s would go up to 2.
And 3p.
And how many do we have left over?
3.
We'd have 3. And if you haven't figured this out yet, the sum of the superscripts should always add up to be the atomic number. Okay? So the sum of the superscripts always sums up to be equal to the atomic number. So we go on to potassium. Potassium now has how many electrons? 19. So we put in 1s2, 2s2, 2p6, 3s2. The 3p now will hold up to 6 electrons. Can we get all 6 in? Yeah, so what's going to come after 3p?
4s1.
Yeah, this is where some of you are going to get it wrong.
4s1.
It's going to go on to 4s1. And so now everybody's going back and they're checking their thing and it's like, well, wait a minute. You just said that we go on to the next highest sublevel. Well, it turns out that the 3D is not the next highest sublevel available. The next highest one available is the, whoops, I don't have it right in here, it's the 4s. Now to help us with this, you have a diagram that's in your packet, I think, this is on the back page, looking something like this. Okay, now what this is showing is, this is showing the sublevels that are available in each different energy level. The 1s has, the first energy level just has the 1s. Second has the 2s and 2p. Now in case you haven't figured out this pattern yet, the first energy level has only one sublevel. The second energy level has two sublevels. The third has 3. The fourth has 4. The fifth has 5. And the fifth one would be 5G. The sixth would have 6, and so on. So if you always want to know how many sublevels there are, the number of sublevels is equal to the value of n itself, at least the maximum number of sublevels. So in the 6 would be 6F, 6G, and then 6H, and so on. They would go. Now as far as the number of electrons in each sublevel, the S's always hold. How many? 2. The P's always hold up to 6 electrons. The D's always hold up to 10 electrons. The F's hold up to 14, and the G's hold up to 18. And you're going, wait a minute, where did you get those? Remember, you already calculated those right here. These are the number of electrons in the subshell. You already figured out what those values would be. So now, the next thing then is, well, why in the world did you put it in the 4s before the 3d? Well, it's going to go back to this little statement that we were writing down. And it's right here. The answer lies right here. And there's two main factors that determine the energies of the electrons found in the orbitals. One of them is the size of the orbital. The other one is the shape of the orbital. So what happens now is that as we go away from the nucleus, if this is the nucleus right here, and we have our 1s and our 2s and 2p, remember the 2p is going to have more energy than the 2s because this has a more complex shape. Okay, so even though they may be the same average distance from the nucleus, because this has a more complex shape, it has more energy than the 2s. So once we get up to the third energy level, we have a 3s, 3p, and 3d. And of course, when we compare an s, p, and d, it's the d that is more complex and would have the higher energy. So now, if we go on to the fourth energy level, we have an S, P, D, and F. Now, while the S is going to be further away, the fourth energy level is further away from the nucleus than the third. In terms of shape, the 4s is one that has a simple shape. The 3d is one that has a complex shape. And because the 4s has a simple shape, even though it's in the fourth energy level, which is further away from the nucleus, the 4s is going to have less energy than the 3d because its shape is much simpler. And so that's why it's important for us to know that there's actually two things that goes into determining the energy of electrons. It is the size and the shape. Well, now after the 4s, things get to be even more complex. And if you ever want to know the order of filling, you do it like this. Here's a little mnemonic, which is a memory aid. And what these arrows represent is if you fill them in, these are the orders in which those sublevels are filled. We start here. We first fill the 1s, then the 2s, then the 2p and the 3s, then the 3p and the 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. So this right here represents the order in which those sublevels are filled. And if we wrote that order out, this is the order we wind up with down below. And you might say, do we need to memorize this? Answer to that question is no. Now the reason why you don't need to is because you have another mnemonic that you'll be using on your exams, and it's called a periodic table. So, in order to figure out how we can use the periodic table, let's go back and look at hydrogen, lithium, sodium, and potassium. Now, what do these configurations have in common with each other? Well, that's not what they have in common with each other, but they're all located in the first column. They end with?
Periods.
They're different periods, but what do they have in common with each other? Look at the configurations. Look what we just wrote. What do those four have in common with each other? Look at what they end with. They all end with S1. They all end with S1. In fact, if we went down to rubidium, if we did rubidium right here, which has an atomic number of 37. If we did rubidium, what do you suppose the configuration of rubidium would end with? S1, specifically what S1? 5S1, exactly. So everything here in this group has an S1 configuration. And if everything in this group has an S1 configuration, that must mean that everything in group 2A must have an S2 configuration. Now we looked at nitrogen and phosphorus. Nitrogen and phosphorus right here. How are their configurations similar? They end with P3. If we look at where they're located in the periodic table, they are both right here. They would end with a P3 configuration, which means everything in group 4A would end with a P2 configuration. Everything in group 3A must end with a P1. Group 16 must be P4, P5, and the last group would be P6, with one exception, that exception being helium, which has a configuration of 1s2. Now, where do you think we're going to find the D's?
The transition metals.
Transition metals, exactly. So we count, we get D1. Remember, D's go up to 10. So we have D1, D2, D3, D4, D5, D6, D7, D8, D9, and D10. And where are we going to find the F's? At the bottom. Those are your inner transitions. And so we count F1, F2, F3. If we go all the way across, we're going to wind up with F14. If you don't believe me, count across there, you're going to find that we have a total of 14 elements going across that streak. Now, when we are in this area, we might go over by about 1 minute. Promise no more than a minute. If we're in this block right here, we refer to this as the S block. These here would be the P block. This here is the D block, and these down here would be the F block. When we are in the S block, we say that they have an NS configuration. When we are in the P block, we say that they have an NP configuration. When we are in the D block, we say that they have an N-1 D configuration. And when we're in the F block, we have an N-2 F configuration. So, if we wanted to now write the configuration, what does N mean? Well, we already talked about N meaning the principal quantum number, but the other thing that N means is the period. The period number and N are the same thing. So, if we wanted to write out the configuration for something like arsenic, arsenic would have a configuration that ends with P3. Specifically, it's going to end with 4P3 because this has an NP configuration. So arsenic would end with, and this is the last one we're going to do here, it's going to end with 4P3. But if we filled in what came before it, it's going to be 3D10, 4S2, 3p6, 3s2, 2p6, 2s2, and 1s2 like this. And if you don't believe me, do the math. But some of these superscripts will add up to be 33, which is the atomic number for arsenic. If you're wondering what the N-1D stands for, notice we went from 4 to 4 here, and this one was 3. So in the D block, we take the period number, which is, in this case, 4, and we subtract 1, and that gets labeled a 3D. And that matches up with the 3D that is right here in between the 4S and 4P. Okay, 1 minute and 10 seconds, I'm sorry. All right, that's it. Have a great week.